Welcome, everyone. We are in data science and technologies, and what I wanted to do today is we were looking at some tutorials. Let me just talk about this article, which I was going to say this I thought was this particular tutorial I thought was very nice introduction to computer vision. And as I say, they do a nice job of just kind of making the case that, pictures and videos are everywhere. And nice explanation of computer vision and image analysis. And here, I'll make this just a tad smaller. Yeah, so, one of the things that, Dr. Dagtus was mentioning is the fact that when we think about how can we get a computer to analyze an image, what the computer is really seeing and among the different file formats is it does understand the idea of having an array. And in particular, we can think of, in this case, here we have array 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So this is basically, 4 by 7 pixels. And certainly the computer can understand this notion that this matrix, what it sees is a matrix of numbers, where those numbers, for example, can represent two colors, black and white. And when we talk about computers making sense of images, it's really looking for patterns in that matrix of numbers that help it to try to understand where there might be shapes or edges or curves, or whether there are certain collections of numbers that might indicate there's some sort of object and what that object might be. Okay. And then we mentioned that what if you had a splash of color? Then what does the computer see? Well, there's been, and as Dr. Dagtus mentioned, there's a number of different color schemes. For example, if we're talking about red, green, blue, this is kind of nice. So what is the computer seeing if we tell it, oh, we want you to interpret color? Well, if you take that 154 red and 205 green and 50 blue, you get this particular color of green. And so in essence, what the computer is working with is a matrix stack. So that's what happens when you feed it a color image. Okay, and of course, the idea is that images can quickly start to take up a lot of space. So if you, and this was just, 28 pixels. So you can imagine if you had a 4K image, how much data would have to be stored. Okay. So, so one of the nice things this article does is talk about some of the basic tasks that we might want to do. And so here's a question, how do you know which pixels represent a face or other objects? And so one of the things you may want to do is maybe you want to be able to identify what part of this matrix is a lizard and what is not. And so this is an example of, they have an image. It is two lizards, and you can imagine that some basic tasks that you might want to do if you're going to be working with image analysis is you may want to for instance, say, well, in that colored image, that's a lot of information. Maybe I would like to turn it into a grayscale. So if we go over to our assignment, yeah. One of the things that Dr. Dagtas had given us is a couple different sets of image challenges. And the first one, the image processing, that's a nice introductory level, and that's the one I'm going to focus on because that's the assignment that I've been playing around with. And last year that was kind of the most favorite. So you can think of this as a scavenger hunt, and the first task is, okay, we have a colored image, and now we want to turn it to black and white. And there are a number of different techniques that you can do to accomplish this, and we'll take a look at some of them. I was going to say there are a couple other assignments. So, for example, these are a little bit more complex. This one is to implement a searching method that allows a person to retrieve images based on the matching of search keywords. For example, this is what Google does. It allows you to give it a picture of a tree, and then it'll go out and try to find similar images. So that is, I keep going a little bit too far. This one is, this one is probably the mid-range challenge, is to see if you can detect the scene cuts in a video clip. And so this is one where Dr. Dagtas has given folks some starter steps. So similar to our cognitive class tutorials, we've got some assignments that are, introductory, medium, advanced. You can kind of, if nothing else, it is just fine if everybody wants to do the basic assignment. And then you're welcome to kind of just even look at the other challenges to see, oh yeah, so here are other challenges or things that people need to work on when they're working with images and videos. And as I mentioned, you want to kind of treat this like a scavenger hunt. So one of the nice things, though, is that you want to start off with an image. This could be an image that you've taken yourself. You can also, for example, pick a topic and say, let me look for, butterfly images. And you can pick an image that you'd like to start off with. And, for this assignment, I think it's just fine. I mean, we're just doing it in the classroom. This is a nice example of fair use, meaning, don't worry, Betty will not get angry at us because, this is not going to go any further, than your homework. Okay. So there's one of the interesting things you probably already discovered with Python. There's dozens of ways to get something done. And so it's a matter of finding the technique that you would like that works for you. So I'm using Google Colab. Some folks might be using Python on their downloaded, like via Anaconda, to their own machine. To do this image assignment, some folks are playing around with a package like GIMP. And certainly even within Python, there are ways to do these things, by writing your own code or by finding a function that will do the work for you. So this was an example of some code that I found. And this one uses pill, and it allows me to actually if you say, so what is this thing right here? Well, this is just, I'll show you what it is. This is an image of a butterfly that is out there on the web. Okay. And what I can do is I can use the image.open function, and I can basically have it to display the image. So that's all I'm doing here. And this is basically, it's displaying the image on the web. Okay. And now I want to be able to convert that image to black and white. Well, there are, again, a host of things. Now, I have noticed, because a few students have already done this assignment, and one thing, if you're going to play around with images, is you may want to play around with what's called OpenCV. And it's an open source. It has over 2,500 algorithms, and it's by the Open Source Vision Foundation. And it has a library with a lot of functionality. So I'll just show you, if you, as I say, there are a number of different solutions, but Google Colab does work with the CV2 library. Of course, we've seen NumPy before. That helps us do a lot of mathematical processing, mathematical functions. And then in this case, we're going to use Matplotlib to help us with, some of the plotting features. And what we're going to do is we're going to read that image. And so in essence, what we did is this was essentially a get function that got this image off the web, and it basically put it into content/image.png. And then that allows me to open up now that PNG image and to display it. So now what I'm going to do is I'm going to read that image. And what I'm going to do is I'm going to use a I'm actually going to use I'm going to use their color function. Now, as I mentioned, there's lots of different ways to do it. One common way of getting a black and white image is you can actually read in the red, blue, and green pixels, add them up and divide by 3. And that, averaging the red, green, blue color numbers is a good way to also convert it to a black and white. And in fact, you can kind of Google, how to turn a color image black and white using Python. Okay, and you get, you can get the code for from CM2. You can find there are other color methods and other from other libraries. You can and we'll just see RGB average. Okay. Okay, there we go. Oh, here's an algorithm that's going to do that by basically getting the pixels and averaging them together. So I was going to say, everything is fair game in this assignment. You can use a product like GIMP. You can use an algorithm like the RGB averaging method. You can use a color library function. That is fine. Part of this assignment is just to let you try out different code and see what works for you. And it does make a difference, what works in Google Colab may, let me put it this way, there are some things that I think that work in native Python that don't work in Google Colab, and probably, vice versa. But this shows you, this is basically using convert color. Here I'm taking the image and I'm doing a color blue, green, red, red, green, blue, and then I'm taking the black and white image, and I'm now converting it to a blue, green, red to gray. And then what I'm plotting here is, notice I'm plotting the image red, green, blue, and I'm also going to plot the image black and white image, and show them side by side. So all of this is just using Matplotlib to print out the results. And I'm just using these two color functions. And as I say, folks are welcome. I'll just leave this. Folks are welcome to go back and play the recording and just freeze it on that screen. So I'll just hover for a moment just so you can take in the code. But that is just one example of how you could get, okay, there's a color image and there's the black and white. All right. Okay. So another thing that you may want to do is the that's in that image processing assignment is this idea of using a Gaussian filter. And what a Gaussian filter will do is sometimes you want to blur out an image a little bit. And here I found, I think, a good, why use a Gaussian filter on images. Let's just see. Okay, and it helps to reduce noise and smooth out details. And basically, it's considered a pre-processing step, and that is you might be wanting to filter out those details because you're more interested in the edges and the overall structure. Let me see if they have some images. Okay. Oh, here's a nice example. Okay. So there you see an example where we're trying to actually, as I say, kind of reduce the details. And again, you'll notice here it is fine. This is one of these cases. It is fine to Google. Again, treat this almost like a scavenger hunt. And as I say, they've got stuff in Wikipedia, and you can Google how to do this in Python. I'll show you how. Here's one solution using the CB2 and in this case, I have all the libraries I need, and I want to be able to plot the before image and the after image. And CB2 has a nice function called Gaussian blurred. And I'm just going to feed it the black and white image. And Dr. Dagtas suggested doing a 7x7. And this is maybe helpful. You might be wanting to say let me just see if I can find. Basically, let me find this. Okay, let me just see. Oh, this is good. Here we go. Let me get images. Okay. So what the heck is a Gaussian, how is this working? Okay, I'll show you what it does. Okay. So this one is actually not a 7 by 7, it's a 5 by 5. That is actually, 5 by 5 is very common, 3 by 3, 5 by 5, 7 by 7. But this is essentially what a Gaussian blur does. And so what it does is think of it as a, it takes your picture and it basically goes through your picture and it's taking blocks of pixels. If you say 5 by 5, it's taking a 5 by 5 block at a time. And what it's doing is it's summing up all those pixel values. So in the case of black and white, you can think of this as all different, variations of gray. And if you were to add these all up, you would get 273. So what they're basically doing is taking these windows of pixels, adding up the pixels values, and then averaging it. And that's how it's accomplishing the blurriness. Okay, so that's really all the Gaussian filter is doing. And of course, what's nice is by using a function, you just give it the image. You tell it, hey, I want to do a 7 by 7. And this one is actually a sigma value, which indicates the standard deviation. And the most common thing that can happen with a Gaussian blur is if you look at these two pictures, it is a little hard to see the difference. But here, I'm going to make this, here's what I'm going to do. I'm going to make this by increasing that 7 by 7 size. You can get it to, here, let me just see if I do it like that and see if you can see the difference. Okay, it's getting a little better. You can also increase this sigma. Oh yeah, and now it's looking, it's actually, not sure if folks in the room, oh well, you can see it a little bit, yeah. So, and it is fine, if you find that you need to just play around with this, just to say, yeah, I wanted to really, make it apparent that it's a little bit more blurry, and that's what you'll often find, depending on your images. Some images are more easy to blur than others. So it is fine to say, hey, I did the 7 by 7, but I didn't see much difference. So I kind of upped the sigma and the kernel size to, just so it was easier to see, oh yeah, that one is, and we can play around. I'm not sure how. Let me see, can we even go, what happens if we, but this is, and the other thing that you'll often find that you, see that's probably, see that you get too much. If you try to blur it too much, it doesn't work. Yeah, so it just seems, let me just see, can I go to 18? Yeah. No, especially just let me back it down a little bit. Yeah, that works. Let me see, can I make this a little bigger too? Okay. But and by the way, the other thing that I found useful is sometimes I will Google on those functions just to find out what the different parameters mean. Because often you find, and I'll just give you an example, if you Google CV2 Gaussian blur parameters, yeah, what do you find? And oh my goodness, look at this. There are a whole bunch of whole bunch of different parameters that you can play with. Yeah, and sometimes it's just, as I say, it's just kind of fun to kind of play around to see, yeah, what the different values do for you. You know. Okay. So that is the Gaussian blur, and then but then thresholding again. So one thing we might want to do with the Gaussian blur is maybe smooth out the background. But thresholding, that is another thing that is very common. So let's suppose that we really want to just focus. We want to be able to just have the computer just pick out the lizard. And so we've got this background and we've got the lizards, and we want to see if there's a way that we can really tell the computer this is lizard and get it to forget about the background. And so usually we try to take advantage of the fact that maybe the object that we want is darker than the rest of the background. And again, this technique will only work if, in fact, the image is darker than the background. So that's something to think about. And so, so one thing that we can do, and this is all that thresholding does, if you think about a black and white image between 0 and 255, we could simply say, hey, guess what? We want to focus on any pixel that's value 130 and above. Because we think 130 and above is basically trying to pick out, the darker things in our image. Okay. And notice they kind of say, hey, this was just an arbitrary number. In real life, you kind of play around because you want to pick a number that would get the most of the lizard while avoiding most of the background. So you can kind of see that there are a bunch of different techniques, but that's essentially thresholding. And in CV2, it's kind of nice. And here's the code, and I think, let me just see, is this all in one line? Let me just see. Okay, let me just see if this works. Okay. Again, all this PLT stuff, that's all just using Matplotlib, because it's kind of nice to see these things. But here I set the threshold value equals 127. And you can see, oh, okay. And you can play around. You can say, well, what happens if I made it 150? Okay. What if I tried to make it, again, part of this exercise is, just kind of play around with it. Oh, okay. Let me try this one. Let me go the other way. Let me try making it 50. Oh, that looks pretty good. So in this case, I think in this particular library, I suspect maybe lower values are black and higher values are light. So so it's interesting. As I went higher and higher, things got blacker and blacker. But when I went lower, yeah. So a threshold of 50. Boy, now if I had really wanted to zero in on the butterfly, that's pretty good. Notice that has gotten rid of almost all the background, so I can just focus on the butterfly. So, again, you just kind of play around, because I've noticed that whole thing is 0 black or 0 white. It seems to fluctuate a little bit between the different tools. Okay, but there you go. Okay, and then the last thing that Dr. Dadtis wanted folks to play around with is what's called edge detection. And let me just give you pre-wit edge detection. And again, but notice here, Geeks for Geeks, it mentions that, yeah, when it comes to edge detection, pre-wit is just one solution on the block. And it's been implemented by various libraries. But what it's really looking is a sudden change in pixel intensities. And so it's kind of looking at, yeah, so where did we go from something like a real dark pixel to a real light pixel? Because that's supposedly, when you can kind of get the sense when you're looking for something like this, how we could find an edge by the fact that, yeah, when we went from dark to light, that indicated a change. So that's the basic premise of that. And it works by having a couple different masks. And so you read the image, you convert it into grayscale if it's colored, you convert it into this double format, you define the mask or filter, you detect edges along the x-axis, you detect the edges across the y-axis, you combine those two edges, and then you display the image. Okay. And notice here, again, lots of sample code. And this was the sample code that kind of worked for me. So I was using the two filters they were recommending, -101, -1, and -100 and 111. Okay. So those were so this is just setting up the masks. And oh yes, and then same thing. You say, oh, so what do all these parameters mean? So all you do is you say, parameters, because you're like, yeah, I have no idea what those parameters mean. Okay. So the first one is the input image. Okay, that's easy enough. So the first, we're just going to start off with the black and white image. Then you see the -1, and you're like, yeah, what the heck is -1? And this is the desired depth of the output image. And if it's -1, the output image will have the same depth as the source. So it turns out you can play around with that. And then there's a bunch of other parameters, but we didn't really have to. But then the other thing that we're going to give is are the masks. And I think what they call the convolution kernel is basically those are our masks, our matrices. Okay. And then we're going to just combine the two. And it turns out you can play with the weights to get different results. And then the rest of it is just plotting. Here's the horizontal edges. Here are the vertical edges, and here's what it has when it combines. And my apologies for folks in the room. We lost our screen, but if everybody has their laptop, if you just want to go into Blackboard, you just need to turn off your microphone and speaker. But if you go into the Blackboard Collaborate Ultra, you'll be able to see the screens right there. And if you don't have your PC, you can also use the back row. Okay, all righty. Okay. Yeah, in EIT 220, We've had trouble with the AV system disconnecting itself from the projector. And we've tried a bunch of different things. We haven't quite figured out what is the problem. Our next thing is we're going to try switching out the PCs to see if, maybe it's the video output card that has started to develop a glitch. But for folks online, you're in good shape, and I think everybody in class has a laptop. So yeah, just go ahead and get into the Blackboard course shell. Okay, but that's the imaging processing, and again, you can kind of I was playing around with these different parameters, just to see what happens when I well, let me just take these down to 0.5. And then just rerun them. Yeah. So you'll notice, depending on how you weight, you get different. You can see how well you can get one edge or the edges to basically come out. Okay. Okay. All right. This is another technique to determine the edges of shape. And we talked about you could use, and the shape, by the way, doesn't have to be a square. There are techniques that use a shape like a circle or a cross. And basically the idea is each pixel is compared to its neighbors within that shape. And here are some of the different terminology you might hear. There's a technique called dilation, and it says if any of the neighboring pixels are dark, then the target pixel is turned dark to match. And so what that looks like in dilation, here I'll make this kind of bigger so folks can see. Okay. So, and this is one using a cross. So you'll notice here in the original matrix, this guy was a 0. So what we do is we apply the cross function, and you'll notice one of its neighbors is dark. So that's why it will turn that pixel dark. And you can almost see this is like a window. It kind of moves across, and if any of the neighbors are dark, it assigns this a 1. Okay. And here's the case of so here's what happens with dilation. And you might say dilation is very good for expanding the borders of objects or filling in holes. And erosion is sort of the same idea, but it's kind of the opposite effect. If any of the pixel's neighbors are a 0, then the pixel becomes a 0. So this is in erosion, if any of the neighbors are 0, then we just say, okay, then the target pixel becomes a 0. And so you can see here's the same, what happens with the same picture if you use erosion, you kind of get the opposite effect. So typically, and sometimes you use them in tandem. So if you do erosion followed by dilations, that helps to remove small protrusions and noise. If you do dilation followed by erosion, it tends to fill in small holes and gaps, and the edges are tidied up. Okay, so you can do things what they call opening and closing. Okay, and often notice we do this in iterations, because we were trying to get closer and closer so we can basically isolate our objects from the background. Okay. All right. So as I say, a lot of these techniques are used, if you will, for the pre-processing. So notice we haven't really identified anything, but what we've tried to do is clean up our images so that it becomes easier for then the algorithms to be able to distinguish, what's an object versus, and being able to ignore the background. But there's a lot of different things now with once your images are ready to be processed, now we want to be able to use techniques like machine learning. And so, for example, on Tuesday, we looked at using convolutional neural networks in order to be able to say, based on this pixel pattern, is this a 1, is it a 7, is it an 8, is it a 9, is it a 0? And so that convolutional neural network would be an example of a supervised machine learning algorithm. And so basically, we're giving them a large number of images and label. And basically, what we're trying to do is get it to identify objects in an image. Okay, so we kind of did that on Tuesday, and notice right there, convolutional neural networks is one example of a machine learning algorithm. Okay, and so this talks a little bit more about how that architecture works. And then, actually, I have Dr. Wu coming in April to talk a little bit about overfitting, but that's when the computer gets really good at labeling the images in the training data set, but then when you give it a new image of a lizard, it does a terrible job of identifying it. Okay, so we kind of, this was kind of the stuff that we did on Tuesday. And a couple of things you can do. For example, of course, we were using classification to identify, what kind of number is this, but you could do it with objects. So maybe you have various animals and you want to classify, maybe you want to come up with a model to predict, is this, is it a fish, a lizard, or a beetle? Okay. Okay. Object detection involves not only identifying the objects present in an image, but also locating them by drawing bounding boxes around them. And so that is, if you want to play with the Google API, that does a nice example. If you have multiple objects, it actually, this is the technique that it does. And notice here, it is identified that in this picture here we go, you just see, so you can see it all. It's identified, there's an object here. It's a little hard to see with the purple, but it's identified this object, which we see is the fork. It's identified the knife. Notice here, it's not really picking up the plate, but it is picking up the main objects on the plate. It's picking up the eggs, the hash browns, and this looks like a piece of sausage. Okay, and as I say, one thing that makes the image analysis time-consuming is typically with supervised machine learning models, all your images have to be annotated, meaning you have a human that has gone through the images and marked up what's in these images. So that is uh, uh, that can be an issue. Also, you have to be a little careful of your choices of images. For example, if I was doing a project where all the dogs were on blue backgrounds and all the cats were on red backgrounds, well, guess what the machine learning algorithm might learn to identify? You know, a red background is a cat, a blue background is a dog, and so it's not really learning what the objects are. It's picking up on, like, as I say, if I was biased in my background colors, it might be learning from that and not from the, you know, what I really want it to focus on. So, and then unsupervised learning in image analysis is basically where we feed it a ton of unlabeled image data and we ask it to extract information and gain a deeper understanding of the underlying characteristics of image. Okay. So this might help us, for example, to locate anomalies or outliers or certain attributes that, you know, maybe we weren't really consciously aware of. And so, but again, unsupervised learning can be an issue because, as you say, you don't know quite how it's going to sort and organize your images. And so, you know, sometimes you can get unpredictable results because, again, you know, maybe it's picking up on things in your image, again, like the color of the background or other objects in the image that may be interfering with actually what you want it to be learning. So, but as I say, but this is like giving someone a bunch of images and letting them sort the images however they see fit. Okay. But it could be useful for things like clustering. You know, go ahead and, you know, group the images by clusters. Sometimes that can give interesting information. Maybe being able to sort the images into meaningful regions or objects, or maybe finding certain patterns. This might be helpful in anomaly detections. So, for example, what's a defect, what's a non-defect? That might be useful. Okay. So that's a nice, so it kind of tells you a little of the different things. And then, of course, a new area is being able to generate new images with generative AI. And of course, that has gotten a lot of press and, you know, questions about deep fakes and things like that. But that's a very good article. And so let me just pause for a moment and just find out, do folks feel fairly comfortable now taking on the imaging, like if nothing else, to do the image processing? And again, you're welcome. You're certainly welcome. Again, it's like a scavenger hunt, and play around, find the technique that works for you. And it is okay to make some adjustments, like just, you know, when I blurred the butterfly, it didn't really look too blurry, so I kind of accentuated the blurriness just to make sure it really stood out as blurry, and it is fine. That is quite all right. And again, this data camp tutorial is a great way to understand computer vision. And I did want to mention that, you know, we've been talking a lot about these convolutional neural networks. However, there are alternatives. So you may have heard people talk about recurrent neural networks, RNNs. And that is a special type of artificial neural network that is good at processing it. It uses, if you will, another, somewhat different architecture for processing data such as text, speech, and video. Another technique is maybe you've heard people saying, oh, well, we're using CapsNet. We're using a CapsNet network. Okay, that's another, a different approach to working with images. You may have heard people talking about GANs. We're using generative adversarial networks. Again, it's in the family of artificial neural networks. It's just if you will, it's another algorithmic approach that can generate realistic and diverse images from random noise or latent variables. And it turns out RNNs can be used for image recognition. CapsNets tend to be better for handling multiple and overlapping objects. GANs can be used for image recognition tasks that involve image synthesis, transformation, enhancement, and manipulation. So keep in mind, as you're kind of looking, let me put it this way, we mentioned on Tuesday, now's a good time to think about, a data science project. And you might be interested in getting an image challenge, and where you can get a data set of images that are ready for processing, and maybe you want to play around. Maybe you want to say, well, maybe I want to test out CNNs versus RNNs, and kind of do an analysis of which techniques seem to do a better job of classifying. And to that end, I wanted to I wanted to mention is that the other thing you can do is we mentioned the different approaches: CNN, RNN, CapsNet, GAN. You want to think of those. Those are really just algorithmic approaches. So that's like me saying linear regression, or that's like me saying or I can say, oh, in addition to linear regression, we've got things like logarithmic regression. And in addition to logarithmic regression, we have things like multinomial regression. And so those are all, if you will, different mathematical techniques. But here's the thing. You can take something like a regression model, and you could take it to R, and you could take it to an R package, and it will do a linear regression model. You can take it to a Python library like scikit-learn, or you can take it to a different Python library like stats model. Or you could say, well, I'd like to do linear regression, but I'd like to use it in SPSS or Minitab or SAS. So keep in mind that on the one hand, you have the techniques, but then these techniques are picked up in these various packages, these libraries. And so notice if you want to do a convolutional neural network, OpenCV will do it. But we saw, on Tuesday that, we could use libraries like TensorFlow and Keras to do a convolutional neural network. Well, guess what? You can go to PyTorch, and it has a convolutional neural network. Or you can go to Hugging Face, or Torch Vision, or, scikit-image. So keep in mind that when you're approaching if you want to do an image challenge, things that you could compare is you could compare, hey, it's kind of comparing, linear regression or, to logarithmic regression. But you could also say, well, wait a second, maybe I want to compare, how TensorFlow does image classifications using the convolutional neural network, and is it harder or easier to do this, using another package? So there are things that you can kind of compare and play with, but this just gives you an example when people are talking about, I'm using people can say I'm using a convolutional neural network and I'm using the TensorFlow library, or I'm using the OpenCV library, or I'm using the scikit image library. And sometimes the vendor can make a difference, because sometimes if you try to, for example, to fit a regression model, sometimes how the different packages have implemented the algorithm can be somewhat different. So, and also in terms of the output and the functionality, and how easy it is to handle certain parameters, that can vary based on how that particular technique was implemented in that set of functional libraries. But I just want to let you know that these are the types of currently popular computer vision libraries. Okay. And then I went out to Kaggle, and I actually said, show me all the computer vision data sets. Okay. They have 3,318 data sets. You can look through these, everything from identifying butterflies, maybe trying to identify, fungus on grape leaves, trying to recognize the weather, being able to say, is this football or is this baseball? This is one looking at, based on the lung, is it COVID or is it not COVID? Jellyfish, identifying cards. As they say, can you identify the celebrity? They have a whole bunch of them. Is a bone broken or not? Brain tumors. They had an interesting one that was, I'll find it. I have it like, let's just see. Is it? Let's just see. I'm not spelling it right. Just see. Okay, there we go. I couldn't spell it right. Villains. They even have one. Is this image a villain or not? Is it a bad guy or not? But anyway, if you're looking for ideas for a project, and you're thinking, there's so many people are talking about, people are talking about, vision analysis. Maybe I'd like to do something a little different than statistics. Maybe you want to go to Kaggle, do computer vision. As they say, they've got over 3,000 computer vision challenges. Look them through, and you just imagine, for your project report, you could, look at something like, this is an interesting one too. This is one for recognizing sign language. And so you can have a little introduction about, why you might want a computer to be able to recognize sign language. You can do a little bit of a background. What did you research on computer vision and American Sign Language? And then you can say, for my project, I'm going to see if I can, create a classifier that would be able to look at various signs and be able to predict what does that sign mean. And then you could go ahead, you could explain a little bit about where the data set came from, do a little bit of background, where did this data set come from. You can then in your report say, which computer vision library did you decide to go with? And then also, which computer vision algorithm did you try out? Did you try out a CNN? Did you try out an RNN? Were there any other techniques that you wanted to compare? And then basically what you can do is you could then run your images and come up with your predictive models. And then you can talk a little bit about, which models seem to perform the best. And then you could finish out with your, closing thoughts. And and then you could have a bibliography where, all the training that you looked at, all the different sources that you looked at, you could have your technical sources and then stuff that you did just to get the background on American Sign Language. And there you have it, right there, you easily have a 10, 12 page report. And it's about the right amount of time, about 40 hours. Okay. Wanted to finish up here, couple interesting things. So in the AI area, I have a little article on digital chips and then versus analog chips. So there you see a digital chip and there you see an analog chip. And this is the one that I wanted you to take a look at. So this image on my left is a digital chip, breaks things down into pixels. But an analog chip would take that same issue and represent it in a continuous fashion. Right now, there's let me put it this way, there's quite a bit of research being done by the chip makers like Intel and NVIDIA on the analog chips. And really, you might say, so why are they, why do they care about analog chips? Well, it's not really analog that's driving it. What's causing the rush is companies like Intel, companies like Analog, Intel is investing in analog chip technology, and then what is it? Is it NVIDIA? NVIDIA is putting is investing in this, and the thing is what they're really interested is coming up with chips that can do AI operations better, faster, and cheaper. And by cheaper, one of the downsides of all this AI is it takes a huge amount of computing power. So we're talking about, server farms having to, really suck up a lot of electricity in order to get all of that AI work done. And so you think you're doing a lot of work, but in the background, there's a lot of processing that's taking place. And so one of the things we're seeing is a lot of the chip manufacturers are looking at really AI chips. And they're looking at AI chips, on a lot of different configurations. But one of the things they're thinking about is that there are certain AI operations that would be faster and cheaper and better on an analog chip set than a digital chip set. And it's not that digital is ever going to go away. It's just some operations will be faster, better on a digital chip, and some operations will be faster and better on an analog chip or some other type of chip architecture that does, that's customized for AI operations. So that is one trend to watch, is that, companies or chip manufacturers are trying to figure out how are we going to keep up with all of this AI computer processing. And one solution is to figure out ways to do these operations in a much more cost-effective, efficient manner. So that is one thing. And the other fascinating thing, I was talking to someone yesterday, Pennsylvania server farm growth. Let me just see. Okay, so it's interesting. A lot of companies now are looking to put their data centers in places that have abundance of cheap electricity. So fascinating enough, Pennsylvania, which I wouldn't think with its cold winters is that great of a place to put a data center, but it turns out that Pennsylvania does have nuclear power plants, and those nuclear power plants are producing, as opposed to solar or wind or coal and gas, is a pretty efficient way of generating electricity. So this is another thing to watch. I think check to see growth of nuclear power due to AI. So this is so interesting. If you're looking to invest, AI goes nuclear. So it's interesting. In order to get enough electricity and power for the server farms to basically generate AI, isn't this interesting? Not only are we looking at new chip technology, but we're kind of looking at new sources of energy. And so of course, modern nuclear is one, and then there's also a lot of interest in, let me just say, yes. The other thing to watch for is, fission is what's currently used in nuclear power, but there have been some breakthroughs in fission. I think there was, an article that in the lab they're starting to be able to do. Fission is currently used in nuclear power plants. It's fusion. It turns out there has been but they're making progress in the fusion area. I think just recently in one lab was able to do the process, producing more energy than what was necessary to create the fusion process. So there's another race on, again, new forms of energy. So anyway, just some interesting things, and we are just about 1 minute left. And then I found this article, yes, some of the future trends. And again, I'll make this, again, this is another article, but particularly for folks who are looking at their doctoral studies, who are trying to think of, wow, what are some of the areas that represent, where I can do new work that's going to build on the work that has been done. And these are just some of the areas that represent future growth. So again, if you're looking at some of the trends that that folks are tracking for the future of this field, that gives you some thoughts. Okay. So that's it for today. So hopefully you're feeling a little bit more comfortable with the image processing assignment. And again, hopefully this material combined with what Dr. Dagtas talked about last week will start getting you maybe more comfortable with the whole idea of computer vision and maybe get you more comfortable with the idea of, what might you like to pick? Aside from just traditional data science, do you want to pick a challenge? Bird versus drone. Lots of great challenges out there. Okay, so with that, we will wrap up and have a good weekend, and I will see you next week.